So why don't we start by you telling us, who you are, what your company is, and why you're such an expert in this stuff, and why on earth would I invite a guy like you to talk about raw, blacksmithing and iron and wrought iron and all this stuff?
I wouldn't say I'm an expert.
Well, you are
My
tonight.
name, I am tonight. Yes, my name is Zoltan Kovacs. Um, I'm Hungarian. That's a Hungarian name. Um, Zoltan is a very popular Hungarian name in the 60s and 70s. Kovacs is also a very popular last name in Hungary. It means smith, blacksmith. And
Really? For real?
yeah,
Kovacs means blacksmith.
it really means blacksmith.
That's just a coincidence. You're not from like 16 generations of blacksmiths, are you?
No, absolutely not. Well,
Got it.
probably, maybe my great grandfather was a blacksmith before. I don't know.
Okay.
I'm a metallurgical engineer by training. I studied engineering in Hungary and in Germany. And it's going to be a fun meeting today, or a fun podcast today.
Yeah.
I learned all the words and everything in Hungarian and German, but not in English. So I will try to explain myself, whatever question you will have. Go around the bush and try to explain what things means and what is in my mind.
No problem.
And I know you want to talk about metallurgy and metals and wrought iron and iron in general. You sent me a quick question about bolts and screws and galvanic corrosions and whatnot. We can talk about it as well.
Good.
It's very important. It's very important to understand the metals and the materials you are using during construction. And you, as a construction scientist or construction expert, you have to know also about metals, because besides wood and marble and stone, metal is a very important part of construction, even decorative and structural. So it's important to know the material what you're using for structural aspect and decorative aspect as well.
Yeah. Well, let me back you up a little bit. So, you get out of college, you've got this super fancy degree, and all of the academic sides of metallurgy. But at some point, you made it to the United States, and if I'm not mistaken, you were working at years ago at Le Métallier Champenois before you started your own company, right?
That's correct. Yeah, they tried to train me as a metallurgist, a metallurgical engineer, and I didn't really practice metallurgy. When I got out from school, I started to work for a foundry. I managed a foundry for 76 people. It was an aluminum foundry.
A foundry?
And I did.
Wow.
As a metallurgist, I specialized for foundry engineering and pattern designs and running a foundry.
Wow.
And not really steel making and not really iron making. But in general, I have some idea about it. I have some idea about metallurgy. It was 30 years ago, so I forgot a lot. And since I didn't, and I didn't use that knowledge,
yep.
It's getting lost. So after that, when we moved to the States, I started my job at Le Métallier Champenois. I was a draftsman. Then I became a project manager. Then I became a vice president for design. And I really enjoyed learning from the Frenchies. Deep knowledge, very deep knowledge. They a lot of experienced people and knowledgeable people. And I somehow I hooked up on forging, what I never studied in the university or school, and shaping the metal different way than I studied. When you are working in a foundry, you melt the metal and you put it in a cavity and create a three-dimensional object. While you are forging, you are heating up to a certain temperature, and you're using tools to form it or shape it. Those tools, either hand tools or machine tools, but it's a different way to approach and different way to form the metal.
So forging is just a general term for reshaping. Am I getting that right?
When we're talking about shaping a metal, you have three different basic ways to forge it. To shape it. One is when you melt it and you put it into a cavity, so you cast it. The other one, when you're heating it up and you're using different shape of tools to shape it and form it, that's forging. Or the third approach is when you are using rollers or also different tools, when you are rolling into a shape, an I-beam or into a tube or into an angle bar. So these are the three basic different shapings.
Wouldn't that just be a variety of forging?
I wouldn't say that, because when we talk about metallurgy, we have to go down to the atoms and the structure of the metal. When we talk about metallurgy is basically physical chemistry, when you have to understand the basics of the material, what you're using. For instance, when you grab a pen and draw a line, you have to know that why the pencil or draw a line, the graphite what is in there, it is making a mark on your paper, but why? Once because the graphite has structure where the graphite molecules can slide on each other, and when you are pushing on a paper with a certain pressure, then those molecules are going to leave a mark on the paper. So you have to go down in metallurgy all down to the atoms and the molecules, and you have to understand the metal, how you're going to forge them. And basically, when you mine the ore and you try to extract the metal what you're going to use in the future, you have to know that metal. You mine the ore for iron, then that ore goes through on a different physical separations to create a more dense iron material, but you can use to achieve the metal.
I'm not crazy.
And
but as a society, humans only figured out how to make iron out of iron ore about 2,000 years ago, right? Plus or minus?
Even less.
Less, okay. So I thought it was like just a couple of years BC, but maybe I'm wrong on that. But anyway, it wasn't like 6,000 years ago. It's fairly recent.
So you create iron, right? And to understand between difference of cast iron or wrought iron, you have to understand how it's made, and how it is created. Basically, the iron is an element, and when you create it, when you smelt it from the ore, it's going to be alloyed. It's going to be alloyed with carbon.
Always, no matter what.
It's always, no matter what.
Okay.
And there's the basic alloy of any iron metal.
Okay.
And I sent you a diagram. It is called I don't know if you have in front of you. If you pull it out, it is very interesting, because that's the basic of all blacksmiths or all metal worker who works with iron, and that's the iron carbon phase diagram, Hayden Sharpie diagram. You will see on that.
What's it called? The
iron carbon phase diagram. Just pull this up, and we're gonna go through on it very quickly, and you will understand the basics of it.
I'm pulling up a different copy, but I got it. You got carbon percent on the x-axis and temperature on the
Temperature on the
y-axis.
Y.
Yeah.
That's right. You will see a couple of lines and showing the different vertical and horizontal lines on this diagram.
Yep.
And also you can see that on the left side from 0 to 2%, 2.14% actually, that usually says steel, and above 2.14% up to almost 6%, it says cast iron. So what does it mean? It means when you creating iron from ore, it's always going to contain some carbon in there. And to work with that, you must lower the carbon content less than 2%. When the carbon content in the iron is less than 2%, then you can work it. You can shape it, you can form it, you can fold it, heat it up to red, forge it, roll it.
When it's less than 2%.
Less than 2%.
And like, I'm not crazy, you know, when they were making iron in the Middle Ages or even earlier, like the Romans, they were down even, that was really low percentages, right? It was all wrought iron, wasn't it?
You never create wrought iron, just clean iron. When you talk about wrought iron, you talk about the steel, which has less carbon content than 2%. And until Martens and or Bessemer steel making technology is figured out, until then they were not really able to control the carbon content in the steel, in the iron. So what they did, they folded it over many times, they worked it over many times, so they were heating it up in the fire, in the coal fire, and just burn out the carbon in there. So it gets less and less carbon. When you are smelting it, you get a bunch of red metal. It's called pig iron. It's a high carbon content iron chunk, and you start to hammer it. You start to heat it up so many times to shape it, and you're reducing the carbon content in there. If you break that, if you break an iron and you see the broken surface gray, that must be a high carbon content. If you see silverish color, that's a lower carbon content. If it is a lower carbon content, then you are able to work it in hot or even cold. You can shape it, you can form it, so it's workable. It's called wrought. Probably it's Old English, workable or working iron, wrought iron. So whatever you call wrought iron, the carbon content is less than 2%. So whatever you.
But isn't that so? I thought that was the number for steel.
So whatever you call steel, you know, this is naming your children, right? what you create, how do you name them? Wrought iron, called long time ago when they were not able to create steels. They've named it wrought iron because they were able to work it, and they called it cast iron or gray or ductile iron. They were not able to work it after it cast, after it shaped, after they got it. So it's called wrought iron because you were able to work it. Then technology just developed, and they were able to control the carbon content. So they were able to manufacture different alloys. They were able to manufacture different carbon contents. They were able to measure. So they named it steel.
Okay,
so if you go back to the 19th.
Anything below this 2% is steel.
Whatever you call steel, It's in 1920s they called it wrought iron. It has less than 2% carbon content. Otherwise,
Got it.
they would not able wrote it. They were not able to work it.
So you just can't work carbon steel when you.
It's gonna break.
Got it.
If you have
Okay.
a cast iron piece, you heat it up, you try to forge it, it's gonna break.
Okay.
And why? This is why you have to know about physical chemistry. You have to know about physical chemistry in that level for the blacksmith even to understand what's the difference between the two materials. To understand that when you have your atoms and your molecules, how it's crystallized, what's going to be the molecule level, how it's going to look like. We can talk about it, phase, how do you call it in English? Phase-centered molecules or structures or cubic-centered structures when the carbon or the graphite atoms are in the center or in the face of a cube, what the atoms shapes. And if you look at that diagram, it's front of me, shows that when you have a certain carbon content and you heat it up to a certain temperature, you will see that it melts in a different level, different temperature, depends on what's the carbon content.
And I'm not. Even in addition to that, its crystal structure changes as you change the temperature. In other words,
that's why you have different type of metals or steels, what you can heat treat, what you can use for different applications. You can make a knife, you can make a tool, you can make a household item or a decorative item. It depends on when you are cooling the metal down, what crystal structure going to be created. If you're cooling it down slowly, quickly, you can temper it, you can make it harder, you can make it softer. It all depends on the carbon content.
So, we're so used to thinking about just water, like, but ice is one thing, you know what I mean? Like you freeze water, it makes one crystal. And no matter how cold you get it or this or that, and then when it melts, it just makes liquid water. Done. So carbon.
I disagree with this because if you put salt in it, the water is gonna freeze at 0 Celsius. If you put water in there, salt in there, like in the ocean, it's gonna freeze below -4 Celsius. If you cool it very quickly, you're gonna get a snowflake. If you're gonna cool it slowly, you're gonna get an ice cube, which is opaque. If you're gonna cool it quickly and there is no any minerals in there, you're gonna get a very translucent ice. So it all depends on what is in the ice, how quickly you're cooling it, and what is the alloy in there, as we say.
So is that the equivalent way to think about steel and iron with carbon in it? A little bit of carbon.
And any metal.
Any metal, okay.
And any metal.
By the way, what happens when the carbon percent goes up really high, like 10% or 20%? Is it?
We measure it up to 6%, 6.2. After that, there is no meaning. I mean, we don't use.
Okay, so
if you go up to 4 or 6%, there are also different. Below 2%, there is carbide, where the carbon is forming. Above 2%, 2.14%, it is forming a different carbon. This is graphite in the iron. When you go to 4%, the carbon gonna be very round shapes. When you go above 4%, it's gonna be very flat. If you put it in the metal under the electron microscope, you will see the difference. And you can search on the internet. You see different structures, different appearance of how the metal looks like, and you can really determine what is the carbon content because of the shape of the picture what you get from the
Really?
electron microscope.
Okay, so when you with the electron microscope, you're looking at crystals basically, and you know from the crystal exactly what the carbon content is. Got it. So
we know what is wrought iron and we know what is cast iron. Wrought iron is what you can work with. Cast iron, what you cannot work with.
got it.
Cast iron, what is above 2.14% of carbon content. Below 2.14, it is steel or wrought iron, workable iron.
I assume though, as you go from 0 up to 2.14%, it gets harder and harder to.
Not necessarily. It's also how you can see that on diagram. There are going to from the molten, the liquid phase in different phases, austenite and perlite and ferrite. Depends on how you quickly jump through on those phases. It's going to be crystallized totally differently, and this is how you can apply the metal for the certain task what you are using for. So let's say you are doing a decorative iron. You don't really care if it is too hard or too soft. What you care if you roll a scroll or for a railing that be malleable and soft for you to be easy to work with. But if you create a structural steel, you have to know that it has to be strong enough to bear the weight and flexible enough not to break. So this is a really complex science to understand.
Now, so if I go buy structural steel from, any distributor, I'm always assuming it's pretty consistent. I can specify a yield strength or something like that. I mean, these days the carbon percent and the crystal content is pretty darn consistent, right?
Since we are able to control more or less how much carbon in there and what we are adding to it, like when we are cooking a soup or making a soup, and shape and having this liquid content to our knowledge or willing, we can control that what kind of metal we're gonna create. But even though when you're purchasing from the same mill, it's gonna fluctuate. It's gonna be always different. So if you are creating something structural or very important things, then you better to receive or get a recipe from the mill, what they are producing, what went through the laboratory and saying that this batch contains this and that, so you will understand what you are getting. Every meal, even though between batches, there are certain differences in percentage of alloys what they are able to produce. So there are certain limits what they can control.
Oh, okay.
So you're never gonna get the exact same soup from the same kitchen.
Got it.
It's gonna be slightly always different.
Now, these days you're doing a lot of what I call ornamental iron, not structural work for the most part, I think, right?
That's correct.
So when you're doing that variety of work, do you always purchase a steel that is the exact same percentage, or do you have to like tailor your purchases for different parts of whatever it is you're going to be making? In other words, you're going to make a flower, maybe you're going to get a really low carbon percent, and you're going to make the kind of the structural parts that are holding it all together at a higher carbon content. Is there any of that that goes on?
We sometimes pay attention to these details, but not so many times. When they say that do an ornamental metal railing, we usually purchase called my steel. The market is requesting to have some fancy names for metals and not really care about what's the metal or the alloy content or what it is. They trust the mills and they say, I purchase an I-beam. I guess 1% of the user is going to check what is in there. It's same for the bronze or brass. We create names what sounds good in the market. Architectural bronze is not a bronze. I don't know if you know that.
No, tell me more.
It is brass. So we create names what sounds good for the application and sounds good for the use, but it is good. Everybody who designs metal works good to know and has to know what it is what they are using for.
Now, if you start dropping some other impurities in with the carbon and the iron, can you still work it? In other words, is there such a thing as like stainless steel that you can still forge? Or
besides the carbon, depends on what you are adding to the metal as an alloy. You are changing the structure of the steel when you are cooling it down. So it's going to crystallize differently.
Yep.
If you look at the pure iron, let's say 0.01% of carbon content, and you're looking at how it's going to oxidize, it's going to create a very strong red oxide on the surface. That oxide is different from those oxides what creates above around, let's say, 1 or 2% of carbon content. Is it a good oxide or not a good oxide? When you say oxide, it sounds good, but when you say rust, it sounds bad, right?
yeah.
If you're looking at the red oxide, what created on the pure iron, it is, I believe, Fe2O3.
Yeah.
It is a very solid oxide which protects the metal from further oxidation. It is like aluminum or lead. When you have on a surface a very hard, very solid oxide, it's not peeling off, and it protects the metal. If you go for the metal where, or the carbon content where the oxide starts to separate and lift off and peels off from the metal, and it's just peeling off constantly, it's really the rust what you are calling rust. So you can scrape it off, and the metal are gonna disappear because it's oxidizing constantly. Can be the rust, can be the oxide is good, yes. Let's say you are introducing for different chemicals and you create a different oxide. It's called magnetite, which is a black color. You call it gum blue or blackened steel. That oxide also protects the metal from future oxidation because it has the chemical and physical structure which is much more solid. So we started this from where? Oh, from stainless steel.
Yeah.
Yeah, we are adding other elements to this steel, nickel, chromium. We are changing the structure of the steel. We are changing the structure in a certain way that it will react for the oxides or the oxidation in a different way. The nickel chromium protects from further oxidations. There is no such thing as rust proof or uh, or I mean what I mean is stainless steel is still oxidizing, as it will show spots or even the entire steel can oxidize, especially when we're going to go to galvanic corrosions, when you are introducing a different material different metal next to it, which is not that noble
Yep.
metal. So this means that even when the construction you are using different metals, you have to know what you're gonna pair and what kind of metals you're gonna use. So we talk about stainless steel. Stainless steel is an alloy where we are putting nickels and chromes and different elements into the steel and trying to create a metal which is more resistible for further oxidation than the steel itself, which contains more likely the carbon itself.
Okay, now to me, the $64 million question. So brass railings. One of my pet peeves is that birds love to sit on them, and then, you know, they create a horrific stain in the railing, you know, when they go to the bathroom on the railing. Is there a non-staining brass? Is there such a thing? Is there an alloy?
Bird poop is an interesting thing.
Yeah, it's a tough one.
It's a tough one. It's tough one because it contains a lot of nitrogen. And
Yeah.
if you want to learn about how they made the swords in Japan back then, a long time ago, you will read about it and you will learn about it that when they force the steel, they always cool it down in the bird poop.
Really?
Because it made it, the nitrogen made it harder and made it much more, I don't know the English word, flexible but not breaking.
Yeah.
So it made it tough. So
I'm just
whatever.
amazed they were able to get that much bird crap together to be able to do that. But okay.
So whatever metal you use and different environment is going to be introduced, it's going to be reacting differently. Let's say you are fabricating a bronze work for New York City, right? Where
Yep.
it is the city environment and also close to oceans, so very salty air and humid air.
Yeah.
That bronze work gonna age differently than the bronze work what you've installed from a different environment. So
Yeah.
the air, the environment where you're using this metal is gonna be always different. Depends on the air, the different elements when you are exposed to.
Right. And that I'm assuming when you go to price a job or to buy materials for a project, you got to study all that. In other words, a project in Denver, Colorado might have very different alloy requirements from a job in Nantucket, you know, where you got a much higher chlorine content in the atmosphere in Nantucket versus Colorado. And it's
What really
right.
have to understand is that what is the when you receive a design or architectural design, you really have to understand what is the use of it, what's the purpose of it, where it's going to be installed, and what they want to achieve in the long term. Some projects are requiring that leave the material aging naturally for a bronze work, just like the Statue of Liberty, turning green. Some clients want to have it always yellowish and brownish color. So you have to understand what they want to achieve, how you're going to protect the metal, how you're going to separate the metal, if you have a substructure to carry the decorative elements. What's going to be the environment exposed to? So you have to understand very first where it's going to be used, where it's going to be installed, what's the decorative part of what they want to achieve in the short and long term. And the next step is to understand that what is the appearance of the metal what you want to create. And the design is always driven by the technology. If we go back to the wrought iron discussion what we had before, when they formed and shaped railings and gates in the traditional way, those days they didn't have electric welding machines. They used forge welding. There are certain ways how to join metals together, overlapping, riveting. In the 16th century in England, they figured out how to do a screw, so they start to use screws and bolts and nuts. And they figured out how to weld with flame weldings. Then later on, the electric weldings came in. And these days, the very popular thing to shape metals are water-jet cutting or laser cutting, and the future is 3D printing and additive shaping. When you are using like a 3D printer, you are welding or adding metal droplets and pieces and shaping creating the forms instead of casting those. So the design is always driven by the technology, and when an architect or a client reaches out to you and asking for a railing, you have to understand what they want to see at the end. They want to see the traditional way how it was forged hundreds of years ago and put it together hundreds of years ago, or they want to cut corners and they find with receiving some railings or gates or ornamental works which is welded together and using some welding marks which is grinded. It's a totally different price tag on the metal work.
So I mean, I'm not nuts. That's really the bigger difference between, you know, what I'm going to call traditional forged ornamental ironwork and modern day, you know, cut and welded ornamental ironwork are all of those little things that, you know, the more practiced your eye is, they're easier to see. In other words, you can see that something's been welded on a modern piece, and you can see that it's been riveted and forge welded on a traditional piece. And arguably a little bit of that handmade imperfection on the forge welded piece, and, you know, absolute sharp corner perfection on the modern piece. Am I getting that about right?
You can get a beautiful marble statue carved by hand by Michelangelo, and you can have the same statue machined with a CNC machine or whatever if it is scanned. If you put these two objects next to each other, some people, most of the people probably couldn't see the difference, but who has a keen eye and they know about the art and they know about the material, they know about the techniques, they will point out right away which is the original and which is the machine made. Do we need the original? Yes, in some level. Do we need to keep this knowledge alive? Yes, absolutely. Do we need replicas? Or what can we afford? What do we want? It has to be what can we appreciate.
Yeah, well, yeah. I mean, if you're putting a, you know, a piece on an outside of a building on the 30th floor above street level, like, maybe you can just weld it because, you know.
Absolutely.
But if it's the front entry gate for your the front door of your house, well, maybe that's the right place to spring for the forged by hand. Is that about? I assume that's about what the way you see it these days.
Yeah, I would say so.
So I've been to your shop, thank you, and I thought it was super cool. Um, and you've got the fire, and they're sticking the metal in it, and the whole thing. But there must be some size limit on that, right? Or do you have like a, you know what I mean? Like, how big of a piece of metal can you work at one time? Because you can go online on the internet and see these enormous pieces that there's, you take a, like you said, pig iron, and they start smashing it with these, you know, 2,000-ton rollers. At a blacksmith shop, there's some limit, right? I mean, but I guess that's the way it was always made. The pieces were always put together from smaller pieces. Anyway, you go ahead. You explain it.
It's hard to explain. It depends on the end result, what you are expecting. Everything can be built up. Of course, there are certain limits what our shop can produce, or other shop can produce. There are different machinery, different tools what you are using to shape them now. But you can always find the right way. I mean, our shop is a very small atelier, but we can create the large gates. We can create large structures. We can create large items. But and just take an example as the Statue of Liberty. Go back again to that topic. We first created in a small atelier, putting it up in small pieces, little pieces, and created something large object. So it all depends at the very beginning when you receive a design for something to decide how you're going to approach and what kind of tool you have to make
Got it.
to create that element. There is no blacksmith shop or atelier or factory who has all sorts of equipment for all kinds of jobs and all kinds of work. So our job is always creating tools and machines and creating all tools to achieve the right shape and the right texture or so.
Yeah. So you're constantly building a tool specific for the piece that you're trying to create at that time.
Every
Wow.
blacksmith does that.
Okay.
So every blacksmith is a tool maker and an inventor. They want to make their life easier, quicker, and depends on how many pieces you have to create. You create a tool for it,
Now,
specific tools for every task.
those hammers that they use, though, how come the hammer doesn't bend or break, but the iron does? Is it just the temperature of the hammer's cool?
Most important is the temperature. The second is the kind of steel what you're using for making your own hammer. But more likely the temperature what you are trying to control. The blacksmiths, the old times the blacksmiths, and these days as well, measuring the temperature by the color of the steel what you are heating up, or the iron what they are heating up, and they are determining how long they can work with and what they can achieve to elongate it or shape it or roll it.
Huh.
So usually a blacksmith shop is not dark because it is dirty or dusty. It is dark because they want to see the temperature of the metal.
I would assume the sound also when they hit it, they must get some sense, right? Or is that something else?
If the blacksmiths can hear it, usually the blacksmiths are deaf a little bit because of the constant noise.
Ay, ay, ay. So, all right. Now, let me think for a moment. So, do you typically see more brass and bronze in ornamental work these days, or more iron?
What I learned in the past 20, 25 years, it is always like fashion. Sometimes the steel and blackened iron became fashionable. Sometimes very modern colors or material comes fashionable. Sometimes the bronze, what designers are preferring. And it is changes every 4-7 years, um, based on
Huh.
the request what we are receiving. These
Got it.
these days I'm receiving more requests for bronze works and less
Okay.
for black and steel or iron works.
Got
But
it.
this is uh, this is by design. This is by fashion. But
Yeah.
what the end users, the owners, are seeing in magazines and newspapers, what they're liking, and if there is more article about bronze works, they want the same.
Got it. And what are there some examples around the country of some really spectacular forged ironwork, that maybe date back 100 or 200 years? Like, I know there's that fence around that park down way at the base of Manhattan there that's not so beautiful, but it's really old. It was there before the Revolutionary War. And I'm trying to think. I can't think of any off the top of my head, but you might know a few. Are there any?
There are a lot of ironworks in the 1920s, especially in New York City. Um, a lot of ironworks were made by different workshops, and it was really an industry, uh, metalworking and ironworking those days, even ornamental or structural when those high-rise started to grow. Um, and still these days are a lot of talented blacksmiths around the United States, creating beautiful objects, not just knives and swords for the show, but
Yeah.
uh, but
But
really things that can be appreciated.
are
Um,
there, are there some
name
places to go look at them though?
Well, there are many museums and places to look at them. You just
Oh,
have to Google that, and many blacksmiths whose name are still out there these days and well known in the blacksmith
okay, but
community.
not like the front doors on the Cathedral Notre Dame in Paris. You're like, wow, that's like, if you want to go look at forged iron, go look at that. Do we have the equivalent in the United States?
Yeah, but if you want to appreciate the Notre Dame forged gate pieces, you will have to also understand that how it was made and why it is so unique. Uh, because not because of the intricate details, but because of the size of it, and to know that it was made at the time when there was no welding machine or electric or flame welding was available, and creating something enormous size and intricate in one piece was a challenge. And some of my colleagues in Hungary, they made a video about it and they published it.
Yeah,
And it was a beautiful thing to learn about it, how it was made and how it was created. So every piece what you hold in your hand, even a candlestick holder or any useful item, if you go to the details and you try to figure out how it was made, it can amaze you if you know the limits of the metal of the material what you are using. So if you want to name one or two uh, blacksmiths or ironwork, I I couldn't, because all of them are what is created. It is unique by itself. I'm not talking about vorage cutting. I'm not talking about modern machinery. I'm talking
huh,
about the hammer and the anvil, what you can
right.
create.
Yeah, handcrafted material. Now, how long, if you get some kid who's graduates high school, he's 18 years old, he decides he wants to be a blacksmith. How long do you think it takes to get, you know, the the skill to be reasonably good at it?
Lifetime.
Oh, that's all? Okay.
Uh, if you ask a blacksmith, I'm not a blacksmith. Um, I'm not a metallurgist. I'm not a designer. I'm still learning. And even if you ask a blacksmith um, who mastered his craft, he's going to tell you that it's going to take you a lifetime to be a blacksmith. But I would say that if you want to know and create and be by your own in a shop, you will need at least 4, 6, 7 years.
Okay. Yeah, well, all right. That sounds about right. And you're probably going to be pretty strong at that point, right?
I couldn't be a blacksmith, let's say 100 years ago. They were looking at your physics first, and if you were under 100 kilograms, 160 pounds, they wouldn't even hire you.
Wow.
But but joke aside, I think the strength is not the most important thing. The most important thing is to be creative, to understand your metals, what you are using, understand the limits of the craft and the limits of the metal, what you can shape to it.
Okay. All right. Well, look, we've been at this about an hour. I don't want to take up your whole evening.
Already?
Yeah. Any anything you want to make sure you explain to people who might, be interested in this topic before we go?
Just a couple of words for builders, architects, and designers is that even though if you are designing, crafting beautiful buildings and ironworks and metalworks, to they have to also understand the limits. They have to understand the metal, understand how it's made, and why some joinery, some rivets or screws are there, because all of them has functions, because all of them are made for support different tasks. Railings are not made curved because it was more nicer than straight railings, but because of structural things. Scrollworks are didn't made just to decorate the railing, but it's made also to structurally strengthen the entire railing and create shapes which can make the railing stronger. So those things, to understand that when you weld, forge weld, overlap, and you will have a seam line, or you will see a screw or a rivet, it is there for hundreds of years because it has a function. It's not there because it is made to be decorative. It is made to achieve the purpose of the item what you create.
Wow. So let me make sure I fully understand that. So you're saying like an elliptical stair may be elliptical not because that's a beautiful shape, but because the craftsmen that were building buildings and railings and stairs realized that they could make it more functional in terms of like not shaking around if it were curved versus straight.
And if it is curved, it can be lighter design. They can use thinner material because it will be strong enough.
Got it.
And they don't have to use heavy metals for the like for the straight railings.
Is any of this stuff written down anywhere, or I just have to, learn it from old blacksmiths?
I think if you read and you're interested, you will find the source.
Eventually, yeah. I got to keep reading, apparently. I thought I read a lot, but that's pretty cool. I never realized that. I really always thought it was just, because Da Vinci made a fancy curved stair, now everybody makes fancy curved stairs,
It was a purpose. They made a bridge bowing for one direction. It's
Yeah.
not because it looks good, because it's structurally stronger.
Yeah, it's a
There is
great
a
point.
purpose why they are using rivets for the bridges, and not weldings, because it makes it flexible, because it's not going to break, but it's going to move, and the rivet allows the metal pieces to slip. So every joinery, everything has a purpose. It's not because and as I said, technology drives the design.
Yeah. Wow. Fascinating. Thank you. All right, Zoltan, you get the last word if you want it.
Thank you very much for